Well, again, thank you for being here. It's not every time that the organizers get the chance to speak at the events they organize, right? But me and Julio and Davide were very fortunate. Well, Davide not so much because we was supposed to be here. He's only going to arrive tonight, so you will see him tomorrow. But without further ado, what I'm going to talk about is mostly thermal transport and mechanical strength of 2D carbon-based materials. So I'm going to start actually talking about graphene because I couldn't not, and it's an ongoing thing. It keeps surprising us at every opportunity we give it. But what I really wanted to talk about was this interplay between thermal conductivity and elastic modulus. That's something I've been working on more recently with a very successful partnership. Well, if you want to see what we're doing, you can find my website in the physics department, dfte.ufrn.br/my last name, Pereira. And so I guess all of you got here, so Natal is right here. These are some pictures of Natal. I should have showed this before you got here, right? But since you're here, if you haven't seen it yet, this is an old fortress built, 400 years ago. This is the dune. This is the beach, right? This is the hotel. You guys are staying probably around here, and we are probably, I don't know, got lost. In the north side, we have this beautiful bridge that connects the city or the old historical part to the north side. I think there is an excursion plan for Saturday where you might be able to cross this bridge or at least see it from far. You guys are staying close by here. This is the beach. It's very nice, even in the morning at 7 a.m. The sunrise is very early. So Natal is well known for the beach, but also something that not too many people know is we have the largest cashew tree in the whole world. So this is a whole block, and this is they say it's one tree. There is a place you can go up here to look at it, and then inside that's what it looks like. The branches go in and out of the ground, but they claim they do DNA testing and they claim it's all the same tree. And of course, since it's the largest cashew tree in the world, it has giant fruits. There are two unsuspecting tourists here. The fruit is not real, please, right? This is just a joke. But you can see some of those if you go there. Let me tell you a few words about our university here in Natal. We are a public university funded by the federal government. It was formally established about a bit more than 50 years ago. It has 37,000 students enrolled today. The university offers 84 undergraduate degrees and 86 graduate programs. And 3 of these graduate programs are among the best in Brazil in their own areas, right? So the physics program, the material science, and the behavioral neuroscience. A few words about the physics department where I'm associated with. It has today 39 faculty, permanent faculty members. We teach about 300 undergraduate students in 3 undergraduate degrees. One to be a physicist, let's say, one to be a physics teacher, and another one also to be a physics teacher, but you can take online, right? You can get a degree online to be a physics teacher. It's specifically aimed at people far from Natal, far from the capital city. We have also about 110 students in our graduate program, and they're all funded by fellowships from the federal government, mostly working on condensed matter physics and astrophysics. But several of the faculty members in the physics department, they participate in both the physics and the material science graduate program. A few words about the IIP, where we are, the International Institute of Physics. So it's a very special type of institute inside of the university. I think its major role is to promote internationalization of both the university and Brazilian physics in general. It hosts events like this one with an international character. It can be schools, workshops, or other types of events throughout the year. And there are many visiting positions for professor, postdocs, and graduate students. So if you're interested, you can see more information at the Institute website. But let's get started with the good stuff, right? Well, in the spirit of the lectures that were given before, let's say, I have to start with you. Why should you even care about studying thermal transport? Everybody here, I'm sure, has a good reason. Many of the students will tell that is their main reason, right? Because their supervisor told them so. Some of the young faculty like me would say, well, because I need to publish papers and, to get grants, so you have to do something. It's almost the same as the boss telling you to do that. But there are some very important applications for thermal transport, which can be seen as a motivation and should be seen as a motivation to studying it. For example, if you have a material with a high thermal conductivity, you can use it to build cooling devices, which are extremely important for several applications, but of particular interest to me or to many people around the world today, right? To cooling your computers or the processors of the computers. You can also want to have a material with a low thermal conductivity, and these could be used, sure, for thermal insulation, but air already does that quite well, right? But if you have a material that has a low thermal conductivity and a high electroconductivity, you can build thermoelectric devices, and you can fabricate, or you can harvest electricity from waste heat. That's extremely important these days. But besides, you having to do it because people tell you to, and these cool applications, no pun intended, there's also some very nice fundamental physics that you can learn from studying thermal transport. One of them is this interplay between thermal transport and dimensionality that was already mentioned today a couple of times. And the thing is this was already said this morning, but in 1D, right, essentially you have a thermal conductivity that scales with the system size. L would be the length in one dimension. And this exponent, alpha, can be anything between 0 and 1, depending on the model you choose, right? As shown this morning, this alpha can take values like 1/3, 2/5, 1/2, or something like that. If you have a system that is fully two-dimensional, that is, your particles live in a plane, right? Then the thermal conductivity should scale with the log of the lateral dimension of the system. Okay, so imagine if it's a square, size L by L, then the thermal conductivity should scale with log of L. And then if you have a material in 3 dimensions, like a bulk material, when the system is large enough, you reach the thermodynamic limit, right? The volume is large enough, and the thermal conductivity doesn't depend on size. It does converge, or it has a fixed value. But these are all based on model predictions. Okay, this one is observed, has been observed for many years. But these two here have only been available a few decades ago when we started to be able to manipulate matter at the nanoscale, right? And this is where carbon enters. The thing is, carbon is extremely versatile as a chemical element, right? It can form several different structures, or it has many allotropes. So for example, you have here diamond, you have graphite with these hexagonal planes, you have this Lonsdale structure, which I've been told already a couple of times. I've used this slide and people told me, actually Lonsdale doesn't exist anymore. They found that it's metastable, but anyhow, it's still here. You have the fullerenes, right? So you have C60, fullerite, C70, you have amorphous carbon, you have carbon nanotubes, and so on and so forth. So if you want to study the interplay between heat transport and dimensionality, there's no better element than carbon, because you can have carbon materials that are 0D, 1D, 2D, and 3D. We started with graphene because it was what was going on at the time, and graphene is very special because it shouldn't exist, right? You have this hexagonal lattice of carbon atoms, and because it's a two-dimensional crystal, there are arguments why it shouldn't exist, and so on and so forth. But then these guys didn't really believe that argument very much and produce graphene by mechanical exfoliation of graphite, which is, I think, is a very fancy name for something you do with a chunk of graphite and a bit of duct tape. So graphene is very special because it's, although it's only 1 atom thick, is extremely, it's stronger than steel when you apply strain. So it can be used for mechanical reinforcement. It has a very high mobility and electroconductivity, so it can be used for electronics. It does have some very important spin transport properties, so it can be used for spintronics. And it has this very high thermal conductivity, which you can manipulate, so in principle it could be used for phononics. It can do everything, right? And you can grow graphene in several different ways, not only by exfoliation, but by epitaxial growth, chemical vapor deposition. There's a guy on YouTube doing graphene on the blender at his kitchen, right? His wife is probably not very happy with that, but he's doing it. And just to give you an idea, the European Union is investing about €1 billion for the next 10 years in this graphene flagship. They must know what they're doing, right? So let me show you a couple slides about phonon heat transport. People have already done a pretty good work about this today. Just to apply, to show specifically how it would work in a material like graphene. So in graphene, you have 2 atoms in your unit cell. And then if you have n atoms in the unit cell, there are 3 n phonon modes. Phonons are these vibrations of this lattice, right? When you have, this would be a picture at 0 Kelvin when you have finite temperature. All of these atoms are vibrating, but they don't vibrate randomly. They do vibrate in some sort of collective modes. That's what we call the phonons. So how do we characterize these phonons? We have here the dispersion relations for them. So essentially you have a frequency as a function of the wave vector of the phonons. And we are particularly interested in these 3 acoustic modes, which are the modes that go that have frequency 0 at the gamma point, which is at the center of the Brillouin zone, right? In graphene, you have two linear mode, the longitudinal and the transverse mode, and then you have a flexural mode, which are vibrations of the atoms out of the graphene plane, like a membrane. And these guys are very special because they have this quadratic dispersion. This gives all the important, or all the unusual properties or heat transport properties of graphene come exactly from these flexural modes. This is clear now, but it wasn't the case a few years ago. So if you consider in a semiconductor insulator, the acoustic phonons are the major heat carriers. And then you can solve the Boltzmann transport equation as mentioned this morning. And under the simplest approximation you can make, in the end, you can write the thermal conductivity of a material as the sum of the thermal conductivity of each phonon mode, which is given by this product here of the heat capacity, the phonon group velocities, and the mean free path. Now, the heat capacities are easy, or the specific heat for each mode are easy to write, and not difficult. The phonon group velocities are just the derivatives of the frequency with respect to the wave vector. So once you have the phonon dispersion, you can easily calculate this guy as well. Now the difficult part is to calculate the phonon mean free path. So all the enharmonic information essentially is in here. So this is how long these phonons can travel before they scatter with other phonons. And this is the tough part. There are ways to calculate this, but unless you use fairly simple approximations, it gets very difficult to calculate it. But there are other ways of calculating the thermal conductivity without actually solving the Boltzmann transport equation. How? Well, I don't know if you've seen this, but I like this diagram. I mean, I know these guys as well, but so in this book called A Guide to Monte Carlo Simulations in Statistical Physics, David Land and Kurt Biden proposed this thing that now is being called like the Landau-Binder triangle. And the idea is that theory and experiment and simulation play an equal footing on understanding nature, at least when in regards to physics, right? And myself, as a computational physicist, of course, I'm very glad that this is the case because this is what we're going to focus on. We're going to use molecular dynamics to calculate that thermal conductivity. How do we do this? Molecular dynamics, something very simple. We're just solving Newton's equation of motion for each atom, right? So we calculate the acceleration from the force over the atom and its mass. Then we can calculate its new velocity from that acceleration. Then we calculate its new position from the original position, velocity, and acceleration, and so on and so forth. Now, the important thing in molecular dynamics is how to obtain these forces. Okay? What we're going to do here is to use interatomic potentials. There are many types, from the most simple Lennard-Jones potential to very complex reactive potentials. And you can also control pressure and temperature via thermostats and barostats, like Nose-Hoover, Berndsen, and Langevin. And of course, you can choose what boundary conditions you want to use in your simulations. So I'm going to begin with our study of graphene under non-equilibrium conditions. So the idea is I have a temperature gradient over my graphene sheet. This side is hotter than this one, and naturally a heat current will show up from the hotter area to the colder area. To describe graphene, we use the Tersov potential. The Tersov potential was originally proposed for carbon, silicon, and germanium systems in a few papers, a series of PRB and PRL papers around 88, 89. It has this general form here. You have a repulsive term. You have an attractive term. You have a term that involves the angle between three atoms. And you have a cutoff function to make sure that the one atom that is here doesn't interact with atoms that are very far from him. The problem with that is just computational, right? So essentially, the calculation of the forces with the Tersov potential scales linearly with the number of atoms. For graphene, we use parameters obtained by Lucas Lindsay and David Broido. They published it in 2010. Lucas is going to be here next week, so if you're still around, you can see what he has to say about his latest project. And we did all of our simulations with lamps, with a small exception that I'm going to bring up in a few slides. So when we look at that phonon dispersion for graphene, right? So these are experimental values from Newton scattering in highly oriented graphite, so in the in-plane directions, and the linear curves, the black curves are the prediction from the potential. So it's pretty good in describing this acoustic mode. Okay, it's not very good describing this optical mode here, but we're not really worried about him. The heat transport comes mostly from the acoustic modes, and most importantly, it gets the quadratic dispersion of this flexural mode correctly. So how do we do these non-equilibrium molecular dynamic simulations? We're going to use Fourier law, which has already been discussed here many times. Again, we're not deriving this by any means. We're just using it as a means to calculate the thermal conductivity. So the trick here is the following. I'm going to divide my system in three parts. I have the hot area, the hot reservoir, the cold reservoir, and I have the actual system where the heat transport happens. Now, there are different ways to create this temperature gradient. One of them is the so-called direct method. I connect a thermostat here and another one here. It can be a Nose-Hoover thermostat, it can be a Langevin thermostat, it can even be a velocity rescaling type of thermostat. It doesn't really matter that much if I use the parameters correctly, which is not that trivial, but the general idea is I put some energy in the system here, and I take out the same amount of energy here. So that amount of energy is flowing through the system. Knowing the area, the cross-sectional area here, and the amount of time, I can calculate this heat current. There's another way, which is really, really amazing. It's called the Mueller-Platter method. It's completely unphysical, and it reverts the cause and effect, the normal cause and effect relationship. But it also works beautifully. And the idea is the following. I start with the system in equilibrium, right? Everybody's at the same temperature. Then I come to this area here that's going to be the hot area, and I look for the atom with the smallest kinetic energy. Right? Kinetic energy is temperature, right? Or temperature is the average kinetic energy. So I take the guy with the smallest kinetic energy here. I come here and take the guy with the highest kinetic energy, and I swap their velocities. Right? I swap their kinetic energies. And after I do that, a lot of times, what happens is I have a number of particles here with very high kinetic energy and a number of particles here with very low kinetic energy. I created a temperature gradient in my system. It's completely unphysical, but it works beautifully, as I'm going to show. Now, once I have a stable or a steady state heat flux, I can calculate the temperature gradient numerically on my system, and I can calculate the thermal conductivity or at least that component of the thermoconductivity tensor. Right? This limits me a little bit on what I have to calculate each component individually, but it's still good enough. Now the problem is that in the presence of these long wavelength phonons, or the heat carriers in this case, I have to be careful with the finite size effect. So if this part here is smaller than the phonon mean free path, it means that the heat can travel from here to here without being scattered. I'm in the ballistic transport regime, essentially, right? And what I want to do is to start my simulation with a given size, and then I keep increasing the size of that system until the thermoconductivity doesn't depend on size anymore. At least that's what we hope. In general, the inverse conductivity you calculate like this is the inverse of the intrinsic conductivity of the material plus a function that depends on the system size. So we did this actually with periodic boundary conditions. So instead of having a hot reservoir on one side and a cold on the other one, I put the hot reservoir at the center, and then I have two cold reservoirs at the ends of the system. Like this is actually just the image of this guy because I'm using periodic boundary conditions on the simulation. And so the heat flows from here to here and then from here to here. Okay, my heat flux divides in two parts, but since these two parts are equivalent, the heat flux is essentially the same for each side. And if I look at the heat flux as a function of time, this is up to 500 picoseconds of simulation. There is some transient period here, and then it starts to reach some stationary state. And then if I look at a longer time scale, you clearly see that it does reach some stationary state, and that's the heat flux I'm going to use to calculate the thermoconductivity. And I can calculate the temperature at each part of the system, right? So I divide the system with the imaginary boxes, let's say. In each box, I have a certain number of atoms. I take the average kinetic energy of that atoms. That's the temperature in that area of the system. If I do that for the whole system, right, I have low temperature here, high at the center, low again, and then when the system reaches its steady state, the temperature gradient can be calculated just from this slope here, and it must be very close, on both sides. Okay. Yep. It's just the average kinetic energy, right? I'm not sure if I should call it temperature, but it's the average kinetic energy in that region of the system. And you clearly see that it does, it does vary as we expected. Now we go on and we do that for graphene, and what we see is that the thermoconductivity keeps increasing, right? This is for 300K. This is the non-equilibrium method. I actually have two thermostats there, and then we do simulations here up to almost 3 microns, and the thermoconductivity keeps increasing. Look, this is a linear log scale, right? So this is really going, the thermoconductivity is going with the log of the system length, which is good in a way if the material really was two-dimensional. The problem is that we had the equilibrium molecular dynamics results from before these simulations that gave us a thermoconductivity of about 1,000 watts per meter Kelvin right here. So we were very confused when we saw this, and we thought, well, maybe the simulations are wrong. So I went on and I redid the simulations using the reverse method, the one where I swap the velocities, right? And I get exactly the same results. Look, the points are almost on top of each other. They have arrow bars that are smaller than the points. And now what I'm not telling you is that the following. I kept increasing the system size only in one direction, right? I have periodic boundary conditions along this direction here, and I kept the width fixed. So we thought, well, maybe the aspect ratio of the system is very large and I'm seeing some weird behavior. So I went back and performed simulations with square patches of graphene, but still, so the length equals the width, right? But still with this hotter area in the center. We did simulations with up to 11 million atoms. Okay, this was done on the Blue Gene with, 64,000 cores. And clearly, we still have the same trend. So it really looked like the thermoconductivity does scale with the log of the system length. And then we went up to higher temperature because we were doing everything at 300K. We wanted to do at higher temperature, we went to 1,000K, and we got the same type of behavior. This is the equilibrium prediction, and this is the non-equilibrium prediction. So no matter what we did, the thermal conductivity really seemed to be scaling with the log of the system size. Now, this is a good result in a way because, you know, graphene is supposed to be this super ideal two-dimensional material, and then we were getting experimental or simulational results that were exactly what you would expect for an ideal two-dimensional system. On the other hand, we had these really good equilibrium molecular dynamics simulations that showed a finite value for the thermal conductivity regardless of size, of system size, right? So we had to make sense what was going on. One of these results was wrong. We didn't know which one. And then when you are a computational physicist and you're in a situation like this, there isn't much else you can do. You have to find an experimentalist to help you out of the hole, right? And we were lucky enough we started going on to conference and showing those results. And then these guys from Singapore approached us and said, listen, we have experimental results that are exactly like your simulation results, and we have no idea what's going on. So let's get everything together and try to understand what's going on here. The experiments are quite amazing. So here you have this platinum electrode here as well. So you pass a current here, this guy heats up, and the graphene patch is here between these two guys, okay? So it heats up here, here's at a lower temperature, graphene transports the heat here. And they could not only fabricate one of these structures, but they could fabricate structures varying the space between the circuits. Therefore, you could change the length of the graphene patch between them. And then when they did that, this is a linear scale, right? They saw a nice increase of the thermal conductivity with the length, both at lower temperature and at 300 K. And then when we put everything together, these are the experimental results in a linear log scale, and this is our simulation results at 300K and then 1000K. And the thing is, in the experiments, the things are a bit more complicated. There is an issue on how to determine the thermal conductivity between the graphene and the platinum electrode that's on top, right? So they didn't really know how to do it, so we had to estimate different values, but regardless of the value we estimated for that interface thermal conductivity, we see this behavior of the thermal conductivity scaling with the log of the system size. So that's it, you know, there is a length-dependent thermal conductivity, at least in suspended graphene. We put it all together, we sent it to a nice journal, and we had to explain it somehow. So one thing that we tried was to look at the vibrational density of states. So it is calculated as a Fourier transform of the velocity autocorrelation function. And I'm just showing it here an example for graphene with zero, just carbon-12, and then 10% carbon-13 and 15% carbon-13. You see this displacement of the G-band of graphene. It has been observed with Raman scattering, you know, experimentally. It's very high precision. So what we did was to use this vibrational density of state to calculate or define a population ratio between non-equilibrium simulations and equilibrium simulations, right? These factors of 1 here are just to normalize this thing such that if this delta n is smaller than 0, you have a decrease in phonon population. If it's larger than 0, you have an increase in phonon populations. And then we calculate this change in phonon populations at several different parts of the system. And then what we see is that clearly you have perturbations, particularly in the longitudinal acoustic mode and the flexural acoustic modes, right? So we have an increase in the population of these flexural modes and a decrease in the longitudinal modes. Now, this is really not proof of anything, but it's just showing us that when you have these non-equilibrium conditions, it changes really let's say, your phonon population throughout the system, and then you wouldn't really expect the equilibrium results to give you the right answer. That was our conclusion, right? So when we compared our EMD and non-EMD results to the experimental data, we realized which one of them was right. Now we find this size-dependent thermal conductivity, and we see that it diverges logarithmically with the system size, as predicted for an ideal to this system. Now, for me as a physicist, a length-dependent thermal conductivity is something almost offensive, right? I mean, this is not a model system. It's a system. It's something that exists in the lab. You can actually go there and measure it. It can't be length-dependent. And luckily, other people thought about that as well. So the group of Francesco Mauri and Nicola Marzari came up right after we published our paper. We published in April. In October 14, they came up with this paper. And what they did here was essentially to solve the Boltzmann transport equation in a very, very sophisticated, self-consistent way. And what they saw was the following, right? So this is the results we had seen. And so essentially these are the non-equilibrium results, and these are the equilibrium results. So they saw that if you consider only single phonon excitations, the thermal conductivity does seem to converge with system size for much smaller systems. But then if you consider the phonon, also these collective phonon excitations, then the thermal conductivity appears to diverge with the system size, with logarithmic with the system size, up to 10 micrometers, and then it changes. Our experiments were exactly in this range. The simulations were up to 3 microns, and the experiments were up to 9 microns. So if we had gone a bit larger, we would have seen what they eventually proposed. Now, the thing is, the thermal conductivity of graphene does converge with size eventually. It's just that you have phonons with, or phonon modes with mean free pass of the order of hundreds of micrometers. So you need a graphene patch of about 1 millimeter to obtain the limiting value of its thermal conductivity. We were very worried because it meant that we couldn't use molecular dynamics to calculate thermal conductivities anymore. Luckily, Luciano Colombo, who will be here later this week, had a really nice idea to study, to calculate the thermal conductivity with an alternative non-equilibrium molecular dynamics simulation. They called it the approach to equilibrium MD. And the idea is the following. You start with the system divided in half at lower temperature here and higher temperature here, and you see how the system thermalizes. From that, they can extract the thermal conductivity, and doing that for different sizes, right? They calculated these red points here, and this exact BT is the solution from the previous paper I just showed you, and then you see thermal conductivity is on safe ground, okay? So it does give you the right results as long as you do your simulations carefully enough. In fact, just recently, we went back and got our previous MD results. So here the direct non-equilibrium and the reverse non-equilibrium. We performed new simulations, right? And we used this expression to fit the thermal conductivity as a function of length. And we see that we obtain a thermal conductivity for graphene at 300 K of about 3,100 watts per meter Kelvin. Look, this is 1,000 microns, so this is 1 millimeter, as predicted by Marzari. So in hindsight, we were right. We just didn't look for systems that were large enough. So the thermal conductivity does converge, or it diverges logarithmically up to 10 micrometers, but it does converge for graphene patches of about 1 millimeter. But still, I mean, so equilibrium D is just wrong. You just throw it away. You can't calculate thermal conductivity with it anymore. Well, I was almost ready to accept that fact. And then I went to a very nice workshop in Lapland. And I met Ari there. And then he said, I explained to him the problem we were having of this discrepancy between equilibrium and non-equilibrium MD results. And he said, listen, you know, there's a postdoc working with me, a very smart guy. I'm going to ask him to have a look at it. And then, well, Ari will be here also later this week or maybe next week. And then Jae-yong went on and had a look at the expressions that people were using to calculate. So the expression for the heat flux in equilibrium simulations. And there were many different expressions. Everyone used whatever they preferred. Now the thing is, in this paper here, we took all these different formulations and showed that they are all equivalent, with the exception of the expression that is used in lamps. So the heat flux expression that is used in lamps is based on a decomposition of the atomic stress, which is only really valid for two body potentials, like Lennard-Jones. It's not valid for many body potentials like Stirling-Weber, Tersov, Reax, or whatever. So you cannot calculate the heat flux in equilibrium MD correctly from lamps. When we did use the correct expression, we obtained a thermal conductivity of about 3,000 watts per meter Kelvin with equilibrium MD, which is within the arrow bars. It's the same as we obtained from non-equilibrium MD. So the results do agree. We are finishing up this paper, and we should send it out soon. So as long as you use the correct expression, the heat flux, the correct expression for the heat flux, equilibrium MD and non-equilibrium MD agree. This is massive because it's been a 5-year quest, let's say. I started working on this in 2011, and I was almost ready to throw the towel. Now, let me use the remaining time to talk about other two-dimensional materials. This is something I did with David that we never really published. We got this graphene sheet, and we made a crest with it, right? You just compress it, and you make this crest, and then you can replicate this. And we calculate the thermal conductivity of this thing with non-equilibrium. I heat it up here, and I cool it down here. And we see the thermal conductivity as a function of the length of this thing. It does converge to a finite value. There's no weird behavior here. And the reason is just that the Phonon mean-free path here is much smaller, right? You have all these crests. The heat doesn't propagate very well. You can see the thermal conductivity is much lower. Now, I really like this sentence. It was in the first solid-state physics book I've ever seen in my life. And it says, crystals are like people. It's their defects that make them interesting. Inspired on that, and then on a paper from Yannick Maya's group that I saw late last year, we did our next work, both with Jae Young and with Bohaira, who is an expert in mechanical properties, and is the person I've been collaborating more frequently these days. And what Yannick Maya's group did was the following. They took perfectly nice graphene, pristine, really high quality graphene, and they destroyed it. They irradiated with these gallium ion beams, and they made a bunch of defects, but in specific areas of the graphene patch. So you have here pristine graphene, you only have hexagons, and then you amorphize a certain area, and then you start to have pentagons and heptagons and even octagons somewhere. Okay? So they took perfect graphene and they amorphize it. And then what we thought was, okay, let's look at what about the thermal conductivity and the mechanical properties of this thing. Now, first thing we have to do is to amorphize our graphene in our computer, right, in the simulation. And our way of doing it is introducing stone whales-like defects. So stone whales are 90-degree rotations of a bond in the graphene sheet, right? So, for example, if I have this bit here, these 4 hexagons. If I rotate this bond here, I end up with something like this. Now I have 1 pentagon and 2 pentagons and 2 heptagons. And I could rotate, again, another 2 bonds here. And then I end up with octagons and pentagons and heptagons and all sorts of carbon polygons, right? We do this a whole bunch of times. We define a defect concentration as the ratio between hexagons and non-hexagons that are left over in the graphene patch. So here we get a 50 nanometer by 50 nanometer graphene patch, and we introduce a 35% defect concentration. Looking from up close, it looks like this, and then at 300K, it crumples. It gets a lot of these ripples because some of them are because of these defects. So first thing we did was to stretch it. We start stretching it in this direction, and up to 12%, that's when we start to see some breakage. If we look very close, you start to see the formation of these large voids. And then if we keep stretching from there, eventually it breaks. When we calculate the stress-strain curves as a function of the defect density, we see that as we increase the defect density, right, so the failure strain increases. So the material, it starts to break sooner, but it only really fails at a later or at a higher strain. Okay, so we also look how it depends with temperature. So this is the elastic modulus and the tensile strength, the strain when it breaks. As we increase the temperature, they both decrease with temperature. Sorry, with the defect concentration. We increase the defect concentration. This is the tensile strain, right? Is the stress at which it breaks, and so it decreases with the defect concentration. But regardless, this thing at 300K still has an elastic modulus of 500 gigapascal. This is 50% of graphene's elastic modulus, so it's very high. Now, we went back now that Zhe-Yong had fixed the expression for the heat flux. We could use equilibrium molecular dynamics simulations, and there's a very practical reason here. We couldn't do non-equilibrium simulations because this thing is highly defective, and we are straining it. And as you do it, and you impose a temperature gradient in the system just breaks down. Okay, so we couldn't do non-equilibrium simulations. We had to do equilibrium simulations, but we used the correct expression for the heat flux, and we calculate each component of the thermoconductivity from this integral of the heat flux autocorrelation function, which you already seen today more than once. And then when we do that, as a function of the defect concentration, we see that the thermoconductivity decreases with the defect concentration, as expected. But it doesn't seem to depend much on temperature, okay? So in this higher defect area here, 20%, 30%, almost 35%, the thermoconductivity is almost insensitive to temperature. And this is very characteristic of systems where the thermoconductivity is fully limited by defects. Now, the thermoconductivity is also much lower than in graphene, and we tried to figure out if we could show why it was much lower. I mean, sure, it's a system full of defects. The thermoconductivity is going to be lower, but where exactly is the reduction, right? And we see a severe reduction in the phonon group velocities, right? So we know that the mean free path is decreasing, but we also show that the group velocities decrease considerably. Therefore, this is amorphized graphene, and this is pristine graphene. And look, this is a log scale for the phonon frequencies, right? So the thermoconductivity of defective or amorphized graphene is much lower, not only because of the phonon mean free path, but also because of the phonon group velocities. We also looked into which kind of defect was worse for the thermoconductivity, or at least for the group velocities. And we see here that these 5-8 rings, or pentagon, octagon rings, have lower phonon group velocities in general than when you only have defects that are like pentagons and heptagons. If I do a graph of thermoconductivity as a function of elastic modulus, right? So this is in a log scale, my thermoconductivity in watts per meter Kelvin, elastic modulus in gigapascal. Graphene is up all the way up here, and this amorphized graphene is down here. Now, there's plenty of 2D carbon beyond graphene, and what I'm going to try to do is to keep adding points to that graph. Okay? So the next point we added was from nitrogenated holy graphene. The authors didn't really call it nitrogen holy graphene, they call it nitrogenated holy carbon, two-dimensional carbon structures. Now, these people actually produced this in the lab, right? So this is produced via wet chemistry, and it's a structure where you have a bunch of hexagons, but some of them only have carbon atoms, and some of them have carbon and nitrogen atoms. The phonon spectrum of this thing is here, so we see no negative frequencies that Hugo was so worried about. So we know that our potential works for this material. This is a new material. In principle, the potential didn't have to work, but it does. And then we set up hot here, cold here. We calculate the thermoconductivity as a function of the system length for different temperatures. We fit with this expression from which we extract not only the intrinsic thermoconductivity of the material, but this effective phonon mean free path. Now, this is not the mean free path of each phonon mode. Each phonon mode has its own mean free path, but this is an average of them all. Okay? This is, it's not very important, I mean, it's not very informative if you want to know about the specific phonon modes, but if a material has a large effective phonon mean free path, it should have also a large thermal conductivity. Skip this. We also look at the mechanical properties of this guy, right? So everything I've been doing with Bohaira, you know, he does the mechanical stuff, I do the thermal transport stuff, and then we look how it breaks. This is really nice. And then we look at, as we increase the temperature, right, the system becomes more brittle, or it breaks, or it fails before. Now, so when we calculate the elastic modulus of this thing and the thermal conductivity, now nitrogenated whole graphene is here in our graph. Okay, so it has a not so low thermal conductivity and a not so low, and a low elastic modulus. Compared to amorphized graphene, which has a high elastic modulus but a low thermal conductivity, right? You could choose either one, for example, if you wanted to use them for reinforcing a polymer and you want the polymer to get stronger but not become a good thermal conductor, or you want it to become a thermal conductor but you don't really care about the mechanical strength of the material. The next point in our graph comes from a material called graphene. Unfortunately, this one has not been synthesized in the lab yet. Now, it looks like this. It has hexagons, pentagons, and heptagons, sorry. That's why it's called graphene, penta, hexa, hepta, graphene. And it was proposed by these guys late last year in Nano Letters. And what they did was a search of all possible structures with a certain number of carbon atoms in the unit cell, or in a supercell. So they calculate the enthalpy per atom, and they number here each structure with a given number. Now, graphene is down here, and what they see is that this graphene is not very far from graphene. Okay, so in principle, you know, the energy of this structure is such that it could maybe be synthesized in the lab. You just have to do your chemistry right. Again, we looked at the phonon dispersion of the material. We see no negative frequency, so we know we can go ahead. We calculate the thermal conductivity. And what we find now is that this material does not have an isotropic thermal conductivity, which means it makes a difference if you conduct heat in one direction or in another direction. The difference is not very large, but it is there. Okay, so in a given direction that we call the armchair here, in analogy with the graphene one, you have a thermal conductivity of about 220 watts per meter Kelvin, and in the other direction about 290 watts per meter Kelvin. We also expect the material to have an isotropic elastic strength, and this is indeed the case. It breaks differently if you strain it along what we call the armchair direction or along the zigzag direction. And then we summarize all of these guys here, and then I go to my graph and I put graphene here. Okay, so it has two different values for the thermal conductivity, but also two different values for the elastic modulus. Well, there's plenty of 2D carbon beyond graphene, including the ones that don't exist yet. Since we got into this game, we considered other possible carbon structures. So this one is a Hackelite. This is not new. It's been proposed about 20 years ago by Terrones and Jean-Christophe Charlier. But then there are also these structure that has squares, hexagons, and octagons. There's this structure that only has these squares and octagons. These all possible carbon allotropes. They are hypothetical. They've never been synthesized, but you know, we just want to see what happens to where they fall in our graph. Now, the good thing about this is that we did our homework. We look at the enthalpy versus the enthalpy for each one of these structures, right? And graphene is here. It's in this line. Graphene is the one we just did before. It was here, right? This is 0.2 eV per atom. Now, if you take that graphene with squares, hexagons, and octagons, it has the same enthalpy of formation as graphene, so it's as likely to be synthesized. And then we have these other two guys here with higher energies. These are a bit more of a stretch. I mean, I don't have any hopes of ever seeing these things around. Again, we go on and look at phonon dispersions. We see no negative frequencies, so we know we can use our potentials. And then first I calculate the thermal conductivity as a system of function of the system length. So the data points are simulations, and this curve here is a fit with this expression from where I extract the intrinsic phonon thermal conductivity and this average phonon mean free path. When I add the 468 structure, again I find an anisotropy in the thermal conductivities. And then when I add the Hackelite, the 567, there appears to be a very small anisotropy here in this case, but it's less than 10%. And then I'm not including the arrow bars here, but they are around that order. So I wouldn't say that this material has anisotropic thermal conductivity. Now when I add all of them to the graph, the 48 falls here, 468 is here, and the Hackelite is here. So what I want to do is just to really verify this trend here, and maybe, if I have enough points, I can even determine a little better what's the form of this dependence. Just to finish, we also looked at other things that are not made of carbon. For example, boron nitride. That's polycrystalline boron nitride. This is what happens when you grow these 2D materials by chemical vapor deposition. Here the average grain size is 10 nanometers. Here it's about 2 nanometers, harder to see the grain size here. And we calculate the thermal conductivity with equilibrium MD as a function of the grain size, and we see that as we increase the grain size, the thermal conductivity increases. So if each patch is larger, the phonons can propagate longer within the patch. We mix this with some finite element modeling, because then we can predict the thermal conductivity for systems with much larger grain sizes than we could do in our simulations. Okay? The interesting thing here is that if you have grains of about 200 nanometers, the thermal conductivity of a polycrystalline HBN is 90% of the thermal conductivity of pristine BN at 300K. So if you need a material with a high thermal conductivity, even if it's not monocrystalline, you just have to make your grains about 200 nanometers, which seems to be feasible, at least for this material. Another thing we did recently was mixing graphene and BN. This was produced experimentally a few years ago in a Giants group, and they just looked into producing this thing and a few physical properties. Now what I've been working on with PhD students I'm supervising is the thermal conductivity of this type of material. And what we see here is that as we change the size of the graphene and the boron nitride patch, we get different values for the thermal conductivity of the ribbon. Okay? So we begin with a high value for a small period, and then we increase the period and the thermal conductivity decreases. We increase the period a bit again, it decreases again, but then when we increase the period again, the thermal conductivity goes back. Okay? So it's a non-monotonic dependence. The thermal conductivity has a minimum at a certain period length. We are working on explaining this behavior in terms of coherent and non-coherent phonon transport across these interfaces. Now, to conclude, I'm still on time. Whatever properties you want to find in a material, there's probably a 2D material that has that for you. And just to show who is the group, Troma is a postdoc I'm supervising, Zach is a PhD student, Gustavo, master students, Fabrizio, Jonathan, and Rafael are undergrads that I'm trying to keep on the right path. Davide Donadio was the person who gave me the opportunity to start all of these things back in Mainz 5 years ago. Bohaira is the person I've been collaborating with more frequently in the last few years. Timon Rabsuk is a professor in the group where Bohaira is located. Ari and Zhe Yong have helped me trying to figure out that discrepancy between equilibrium and non-equilibrium results. David and Ari will be here later this week. And, geez, that's it. Thank you.